All right, welcome to The Explainer. Today we're diving into a really big question, a huge one actually. How do we build a 100% clean energy grid that doesn't fall apart? And it turns out the solution isn't just a patch-up job, it's a brilliant upgrade to the whole system.
So really, how do you go about replacing these giant spinning machines that we've relied on for, a century with silent solar panels and wind turbines, and do it without making our power grid dangerously unstable? I mean, the engineering behind this it's truly fascinating.
Okay, so to really get the challenge here, we first have to talk about the grid's unsung hero. Seriously, there's this hidden force that's been keeping our lights on for over 100 years.
And that force is called inertia. And for the electric grid, this isn't just some concept from your high school physics class, It is a physical reality. It comes from these absolutely colossal, multi-ton turbines and generators spinning away inside traditional power plants, all perfectly synchronized to the grid's frequency.
Yeah? That freight train analogy? It's perfect. Think about it. That immense rotating mass acts like a giant shock absorber. So if a power plant suddenly trips offline or some huge factory powers up and creates an imbalance, the grid's frequency starts to drop. But all that physical inertia, it resists that change. It slows everything down, buying precious seconds for other power plants to kick in and stabilize the whole thing. It is literally our built-in safety net.
Okay, so if this system has worked so well for so long, what's the problem, right? Well, it turns out the very technologies we need for a clean future, they're the ones that kind of throw a wrench into this old mechanical system.
Look, solar panels and wind turbines are absolutely incredible, but they just don't have those huge spinning generators hooked up directly to the grid. Instead, they use these electronic devices, inverters, to convert their power into something the grid can use. We call this asynchronous generation, and the key thing is it lacks that physical rotating mass.
And that right there is the core of the problem. As we replace the giant freight trains of the old power plants with these new electronic sources, we are systematically removing the grid's natural shock absorber. And with less inertia, any little disturbance can cause the grid's frequency to change dangerously fast. I mean, really fast.
But this is where the story takes a really brilliant turn. Instead of trying to rebuild the old mechanical system, engineers realized they could create something way, way better.
It's called synthetic inertia. And get this, the very same inverters that connect renewables to the grid, these incredibly fast power electronics, they can be programmed to watch the grid's frequency and react in microseconds. We're talking injecting or absorbing power instantly to counteract any changes.
And this comparison right here, it just brilliantly illustrates the upgrade we're talking about. See, natural inertia is a passive physical reaction. It just happens because of mass. It's clunky. But synthetic inertia? That's an active, intelligent response. It's driven by software, it's instantaneous, and it's precisely controllable in a way mechanical systems could never, ever be.
And they do this in a few really clever ways. They can either hold back just a small percentage of their power, ready to be unleashed instantly when it's needed, or they can pair up with batteries for that quick jolt. But what's truly incredible is that tests have already proven that solar plants using these tricks can provide a better and faster response than the fossil fuel plants they're replacing. So let me say that again. This isn't just a replacement, it's a full-on upgrade.
So we have the technology, which is awesome, but to build a reliable grid out of millions of these devices, all from different companies and manufacturers, well, everyone's got to be following the same set of rules.
And that's where IEEE 2800 comes in. This is a total landmark standard, the first of its kind for North America, and it basically spells out the baseline capabilities that all new large-scale solar, wind, and storage plants have to reliably support the grid.
Yeah, the best way to think about this is like a universal traffic code. It just makes sure that every vehicle on this energy superhighway, every single power plant knows exactly how to behave during a grid traffic jam or, a real emergency.
Now, here's a really key distinction the standard makes. It's the difference between capability and utilization. So IEEE 2800 makes sure the power plant, let's call it the car, is capable of performing all these advanced grid support tricks. But it's then up to the grid operator, the one setting the speed limit, to decide how and when to actually use those capabilities. This standard also solves what has been a persistent headache for grid planners for years. See, in the past, there was often this gap between how a plant was supposed to perform in a computer model and how the as-built plant actually worked in the real world. IEEE 2800 creates a common, verifiable baseline. It closes that gap and gives grid operators the certainty they desperately need.
All right, so what does this all mean? What does this new rulebook actually do for our clean energy future? Like, what's the real-world impact here?
Well, let's take a look at the grid in Texas, for example. A gap analysis by the operator there, ERCOT, found that IEEE 2800 fills at least 13 high-level gaps in their old requirements. We're talking about things like fast frequency response and dynamic voltage support, functions that are absolutely critical for stability that will now be standard, built-in capabilities.
And this impact, it's not just local. I mean, the International Renewable Energy Agency has already pointed to IEEE 2800 as a global blueprint, a model for the entire world to follow as we all build out the next generation of power systems.
So really, it all boils down to this incredibly powerful combination. We have the advanced technology to make renewables active, intelligent supporters of the grid, and now we have the Universal Rulebook to make sure that tech is used safely and reliably, everywhere.
And this pairing, it allows us to accelerate the transition to clean energy without sacrificing the rock-solid reliability we all depend on. It's proof that we can build a future grid that isn't just clean, but is actually more resilient and more controllable than the one we have today.
So that leaves us with a pretty exciting question, doesn't it? We have the technology, we have the rulebook. The path to a 100% renewable and 100% reliable grid is clearer than it has ever been. So, what's stopping us? Thanks for joining this explainer.